Okay, so I would like to practice today some matrix multiplication combined with some complex numbers. Now, we won't be doing anything really complicated with either of these, but it's a nice little practice, practicing both of them at the same time. And I'm going to use these matrices called the Pauli matrices, named after a great physicist named Pauli, Italian guy, Wolfgang Pauli. And they're usually denoted sigma x, sigma y, sigma z. Okay, but I'm going to just write them out. So I forget which one is which, but one of them is this matrix right here. And another one of them is this matrix. And another one has I and an I here. Now, before we jump into it, I want to make a few notes for some people. Obviously, the identity matrix is this, and we may be using that as well. But I just want to say that if you have a matrix that is either like this with zeros, or you can switch the negative sign over there. It doesn't really matter. But this works like the number I. It's very similar to the imaginary number I. Why is that? Well, if I multiply this times some vector, we'll give it components x and y, then when we multiply this out, we'll get y upstairs here and then negative x below. And if you imagine that in the coordinate plane, so you had some, let's say you had some arbitrary xy coordinate, it's going to reflect. So what is it doing? First of all, let's switch the y and x. Actually, let's do it this way. Let's look at what does a rotation do? Let's ask ourselves that question. So rotation of 90 degrees will go here, right? Here in this drawing, it kind of looks like I'm reflecting about the y-axis, but not exactly, because this is slightly lower than, like, if this were something where the x and y values are the same, it's slightly below that, and here it's slightly above that, this sort of 45-degree angle line, if you will. So anyway, so this is a right angle. So what are we doing? So I think we can view it as, I don't know, I'm getting confused. But work out some examples and you'll see that this is rotating by 90 degrees and that this is like I. It rotates by 90 degrees. Now, this is kind of out of the scope of this video, but there's this whole business of exponentiating matrices. And I made a video about it. It's about, this is related to Lie theory, or Lie groups and that kind of stuff. So there's some video on my channel about it, but when you exponentiate this, and let's say we have x here, it will come out to this matrix. Now, if there's a negative below, it'll be negative here. If the negative is above, it would be up here. But this is just the difference between these negatives being below or above is just it's a difference between clockwise and counterclockwise rotation. But this is a matrix that will rotate by x. So when you multiply times a vector, you get if you imagine that there's a vector, let's say you're multiplying times a, b, you will get, okay, let's go back a little bit. A, b, it will equal cosine, a times cosine x plus b times sine x, and the next one will be b times cosine x minus a times sine x. And I'm a little tired from making all these videos, but this is rotation. Maybe work out some examples. I'll leave that as an exercise for the viewer if it's unclear that that's rotation. But all this stuff is really interesting, and the fact that this matrix acts like I, and that it can be sort of interpolated or exponential. It can be interpolated through this exponential map. It's very, very cool. But anyway, so when I see this matrix, it's a weird combination of, for me, well, it's like I times the matrix we were talking about. Now, so these are the Pauli matrices, these three, but mathematicians usually, they might use a different set of matrices where you just take these and multiply by I. Is useful for different circumstances. But these matrices are used sort of for historical reasons. It's more convenient for the physicists. But, and then multiply times I here, and we will get -1 and +1. So we could alternatively use these matrices, and I'm kind of indifferent to it, but I just wanted to say that, like, because if you're trying to use these matrices as a basis by doing, these are meant to be a basis. So these three matrices, the Pauli matrices, together with this identity matrix, well, actually, well, in some way they are equivalent to the quaternion algebra, and they're equivalent. They're used for the whole the spin in quantum mechanics. And so we say that these form a basis. And so you can try different things. You can try adding them. You can try multiplying them. You can put them through the exponential map first and then multiply them. There's lots of little things to try to do and play around with. And you can do it with or without this identity matrix as well. And you can do it with these. You can do these versions of them instead. So there's lots of different combinations to try. So let's just try multiplying some of them out for practice. Hopefully yeah, okay. And there we go. So let's just start with this matrix and play around a bit with it. And which other one should I pick? So we have three different options, and we can choose. There's three different ways to choose combinations. Let's multiply times this one. Now, this matrix is interesting. If you exponentiate it, if you pass it through the exponential map, unlike what I showed you before, you get hyperbolic rotation, which is also very interesting. And hyperbolic rotation is related to special relativity, so that's quite interesting. But this is also a permutation matrix, and depending on whether you left multiply or right multiply, it will either switch the rows or the columns in the next matrix. So let's multiply this out. So we get 0, we're going to get I up here. We get 0, 0, blah, 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 0, 0, 0, blah, 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 and we get negative I here. So what happened, it looks like it switched the columns. Or sorry, it switched the rows. When you left multiply, it switches the rows. And as an exercise, you can write multiply if you'd like. It'll switch the columns. Now, I mean, I guess this matrix is the other one that is pretty straightforward. You're just negating the y value. It'll leave x alone and give you a negative y. So, but let's try right multiplying and just try to verify that that is going to do what we think it is. So, if it, yeah, let's see what happens when we right multiply by this matrix right here. Okay, so the first term will be this times this plus this times this, which is 0. Then we get positive I. Then we get I and 0. Oh, okay. Yeah. So what happened? It negated the right column. And I think if you left multiply, it will negate the second row. So you can see this sort of trade-off between where, depending on if you left or right multiply, if it will affect the rows or the columns here with some of these. So I think that, and actually let's do this more generally. Let's just, well, yeah, it's fairly simple, this exercise, but so it's going to be A for the first one, B for the second one, and 0 minus C and minus D. So you can see that if we left multiply, it negates the second row, and if we right multiply, you can do it as an exercise with this general matrix and see that it will negate the second column. And I mean, I don't know that there's that much more interesting to do, but you can play around with these matrices here as an alternative. And I don't know, if you want to practice matrices, just invent some more to multiply around. It's good practice. I'm playing around with matrices all the time anyway, so. But these power lead matrices are kind of fun to play around with, and I think it's good practice. So that's a good place to stop, and have a good one.